Hi, welcome to a demo session in the NPTEL course on Haskell. In the previous lectures, we saw user-defined data types. So let us try to program some of these and gain more familiarity. Okay, so if you recall, we we define data types using the keyword data, and one of the first examples we said was data day equals Sunday or Monday or Tuesday or Wednesday or Thursday or Friday or Saturday, right? So this is what we said. Now one can, let me save this and let us start a GHCA session. Okay, I am starting a GHCA session. Let me load temp.hs. Right now I can ask what is the type of Sunday, right? It will say day, but I cannot just say Sunday. It will create a problem because there is no instance of show for day. So what we have to do is, whenever we define our own data type, typically we will have to say deriving show. Once we do this, then we can actually go here, reload the script, and once again ask for Sunday. This time it will print it, right? Now we could ask whether Sunday equals Tuesday. We expect the value false to be produced as the result of this expression, but there will be an error because there is no equality defined for day. It's a thing that we have defined on our own. So we need to tell Haskell how to define equality for this. So thankfully we don't need to ab initio define equality. So we can just say deriving equality along with show. So typically you will, for most data types that you will define on your own, you will do a deriving EQ show, which will define a default behavior for show as well as for equality. So now what is the definition of equality? There are 7, if you recall, these are called constructors: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So there are 7 such constructors. Distinct constructors are distinct. Okay, so if we go here and once again reload and ask Sunday equals Tuesday, right? Now we get an answer false. Okay, so okay, so let's get back to our code. So if you recall, right, now that we have this, we can actually start computing things like next day or is weekend. Okay, we can do this. and we can say is weekend Tuesday, you will get the answer false. Is weekend Saturday, you will get the answer true. Okay, so you can do things like this even without deriving equality. We can do pattern matching. Okay, if I do not derive equality, I will get an error for this code. If I try to reload, let me go back to GHCI and let me try to reload this code. I am getting an error because it is saying no instance of EQ day arising from a use of equal to. But if I comment this out, if I comment these two lines out, I can give a different implementation of is weekend using only pattern matching. That works even if you do not define it as equality, because pattern matching does not depend on checking for equality. You are just doing a case analysis. If this constructor is this, then do this, etc. You are not actually using the equal to operator. Okay. You could say is weekend Saturday equals true, and is weekend of anything else is false. Yes, such a thing can be defined. Let us go back to GHCI and verify that it compiles. Yes, it does compile. Okay. So the other example we saw was to define shapes. Okay. So data shape is different from day. Day is what is called an enumerated data type. You can clearly enumerate each single value. Each constructor is just a value, but since I mentioned the word enumerate, you can actually in the lectures we saw that you can do show EQ enumerated enum. You can do that, and then you can actually you can you can do things like Sunday till Monday, Sunday till Wednesday, right? You will get Sunday, Monday, Tuesday, Wednesday. That's because you have defined it to be a member of the class enum. Okay, enum is enumerable types. Okay, so you can actually use this kind of list notation. Okay, so shape is once again there are, the way we defined it, there are three constructors: circle. So a shape is a circle or a rectangle or a square. But in each case there is an extra parameter. If it's a circle, I want to give a double as a parameter, which stands for the radius. If it's a rectangle, I want to give a two doubles as parameters, which stand for length and breadth. If it's a square, I will give a double as parameter, which stands for the length of the side. Okay, and I can say deriving EQ. Maybe I won't derive EQ. Deriving show, I can say. Maybe I don't need to derive anything at all. If deriving will define default behavior. If you want to define your own custom behavior, then you should say instance. Instance show shape, where you have to define a small s show function, show circle of R Remember that small s show is a function of type shape arrow string. So I should just produce a string circle of radius, and then I am just showing the radius, right? Show is polymorphic, so show can take anything as input. show for circle works in this case, show for doubles have already been defined. So we say that show of rectangle LB is nothing but rectangle with length show L and breadth and show of square S is square with side length. Right, you could do this. What else can we do? So you can define an area function. This is something that we defined. Area of type circle arrow double. Area, no, not circle arrow double. Area of type shape arrow double. Shape is a type, circle is a constructor, so I cannot have circle arrow double. Area of circle R is pi times R times R. Pi is already defined as part of prelude, we can check it. Right, pi has value 3.1415926 blah blah. So you can freely use pi. Rectangle LB the area of rectangle of length L and breadth B is L times B. The area of a square with side length S is S times S. You could also add other shapes if you want, triangle, etc., etc. Now, maybe, so you want to ask for when two shapes are equal, and you can have the default behavior. If I say deriving, then two shapes are equal if and only if the constructors are the same and the parameters are the same as well. Okay, so having defined this, if I save this Haskell script and if I go to GHCI and reload this, right, I can ask circle 2 equals square 2, even though the 2 is the same, this is a circle and that's a square, so it should say false. I could say rectangle 4,3 equals square or rectangle 3,4. This would technically say false because the first argument is 4 in one case and 3 in the 3 in the other case. Okay, so there is a difference. Even though it's the same constructor, even though it's the same arguments, the arguments are supplied in the wrong order, so it will again say false. But now we can define our own custom ordering also, right? So we can say instance ORed shape. And we say shape 1 is less than or equal to shape 2. This is the definition. So for ORed, for something to be a member of the class ORed, the type should have a definition of less than or equal to. Okay, and this is what we are defining, and we define it to be area shape 1 is less than or equal to shape 2 if and only if area of shape 1 is less than or equal to area of shape 2. This is a cooked up definition, but this is just to illustrate how you can define such things. Okay, it doesn't make sense to compare two shapes and say, is this less than that? But maybe one meaning you can give to that is to ask whether the area of one is less than or equal to the area of the other. Okay. So now you can actually once again load this, and you can ask whether rectangle 4, 3 is less than or equal to rectangle 3, 4, and you will get the answer yes. Okay. Or you can ask whether circle 2 is less than or equal to square 4, and you will get the answer true. Okay. Because pi into 2 squared is pi into 4, but pi is less than 4, so you will get the answer true here. Okay. So you can do things like this. The next thing we saw was that you have you can define complex numbers, and here is how you define it. Data complex so there are two arguments, one signifying the real part of the complex number and one signifying the imaginary part of the complex number. But this is a single constructor, and there are just some values. So if you have a single constructor, then you can use the record syntax. So let's just illustrate the records, and let's illustrate both syntaxes. Data complex equals, notice that I am using complex both for the name of the type and for the name of the constructor, and this is Haskell convention when there is only one constructor. Okay. And what can you do with a complex number? You can actually find out the real part of a complex number. And you can also find out the imaginary part of a complex number. So re and im are both of type complex arrow double, and you define real to be real of complex R anything is R, imaginary of complex anything I is I. Okay. So this is how you can define things. And yeah, so you can also define things like absolute value. Absolute value of a complex number is nothing but the square root of the real part of the complex number squared the imaginary part of the complex number squared. Okay. So you can do this, and you can go and check what the type of. So notice that we have not supplied the type here, just to show you how Haskell infers type. Let's go to GHCI and reload the file, and you will see that suppose I ask for type of absval, it will say complex arrow double, even though I didn't explicitly give the type. Okay. But it is, as we saw in the slides, it's painful to have to define such destructors all the time. So instead we could have used the more friendly record syntax. So in this syntax we would say we would give the constructor, and then we would name the two fields right here. And even though we named it in this, even though we presented it in this format, array and im are both functions. If you supply it a complex number, it will produce a double value. Okay. So that's the point. Let's save this again and run it in GHCI. Okay, so this compiles and I can ask for absolute value of, I don't know, so complex real equals 3, imaginary equals 4, let's say, right. I get the value 5 because 5 is 3 squared plus 4 squared square root. Okay. Okay, so now I could also define a less than on complex numbers based on the absolute value. This is arbitrary, of course, there is no natural order on complex numbers, but I can define it this way. I can say instance odd complex where uh, complex 1 is less than or equal to complex 2. Here we are defining this less than or equal to, and this is of type complex arrow bool. Whereas the less than or equal to that we are going to use on the right side is of type double arrow bool. Absolute value of complex 1 is less than or equal to absolute value of complex 2. Okay. So, this is just like what a mathematician would say, right. So, would say that one complex number is less than or equal to another if and only if the absolute value of the first one is less than or equal to the other. Okay. This if and only if kind of definition is what we are giving here by just saying equality. Okay. So, less than or equal to on complex number is nothing but checking less than or equal to on the corresponding absolute values. Okay. So, let me save this and let's get here and let's reload. Okay, so no instance for equality complex. Okay, we made a mistake. You cannot define OR before defining equality. So let us define an equality by just using the default behavior. Or you could say that, yeah, so we'll just define it like this. And once you have defined, once you have done deriving EQ, now you can actually compile this. Yeah, compiles. And then you can ask whether complex, let's define two complex numbers, complex 1 equals complex 3, 4, complex 2 equals complex 2, 5, and then we can ask whether complex 1 is less than or equal to complex 2. We can say complex 1, let's see how it prints it out just to show, just to see what internal representation it has. We might get an error because we didn't do a deriving show, right? We are getting an error, right? So, let's go derive show. And let's come back to GHCI and reload the function. Yes, it works now. So, I once again have to define these things. Complex 1 is complex 3, 4, complex 2 is complex 2, 5. I can ask for complex 1 less than or equal to complex 2, that's fine. I'll see how it's internally represented. Yeah, so it prints it like this: complex real equals 3.0, imaginary equals 4.0. Okay, in a friendly notation. Okay, good.